Imagine you are trying to teach a computer to predict how water flows through a complex network of pipes. If you used standard machine learning, you would act like a photographer, showing the computer millions of pictures of water in pipes and telling it, "This is what happens when the pressure is high, and this is what happens when it is low." The computer would eventually get very good at recognizing those specific patterns, but it wouldn't actually understand why the water moves that way. If you showed it a pipe shaped like something it had never seen before, or a liquid thicker than water, the standard model would likely get confused and make a guess that makes no sense, such as the water moving from low pressure to high pressure. This is the black box problem of traditional AI. It is brilliant at copying what it has seen, but it is completely ignorant of the rules of the universe. Physics-informed machine learning changes the game by acting less like a photographer and more like a tutor. Instead of just giving the computer raw data, we give it a set of guardrails based on the laws of physics, such as the fact that mass cannot simply disappear or that heat always moves from hot to cold. These laws are usually written as mathematical equations. In a standard AI model, the computer only cares about matching the data you gave it. In a physics-informed model, the computer has two goals. It wants to match the data, but it also desperately wants to satisfy those physical equations. Every time the computer makes a prediction that violates a law of physics, it receives a mathematical penalty, essentially being told, "Your answer might look like the data, but it is physically impossible, so try again." This approach allows the machine to understand a physical phenomenon much more deeply than a standard model ever could. Because it knows the underlying rules, it doesn't need nearly as much data to learn. While a standard model might need 10,000 sensor readings to understand a cooling system, a physics-informed model might only need 100 because it already knows the basic logic of thermodynamics. It can fill in the gaps where sensors are missing, effectively seeing what is happening inside a solid engine block or deep underwater just by calculating what must be happening according to the laws of physics. This makes the AI much more trustworthy for high-stakes engineering because its predictions will always remain grounded in reality, even when faced with a situation it hasn't seen before. In the real world, this technology is already solving problems that were previously too difficult or too slow for computers to handle. In the field of medicine, researchers are using it to model blood flow through a specific patient's arteries to predict the risk of an aneurysm. Since every human body is shaped differently, standard AI struggles to generalize. But because the physics of fluid dynamics are the same for everyone, a physics-informed model can create a personalized digital twin of a patient's heart. This allows doctors to test surgeries on a computer before ever picking up a scalpel. Similarly, in the energy sector, engineers use these models to design more efficient wind turbines. By embedding the laws of aerodynamics into the AI, they can simulate how air moves around a new blade design in seconds, a process that used to take days of heavy computing power. Beyond medicine and energy, physics-informed machine learning is becoming a cornerstone of climate science and infrastructure. It is being used to monitor the structural health of massive bridges by analyzing tiny vibrations. The AI knows how steel and concrete are supposed to behave under stress, so it can detect a microscopic crack long before it becomes visible to the human eye. It is also helping meteorologists create more accurate weather models that respect the complex laws of atmospheric pressure, leading to better early warning systems for floods and storms. Ultimately, this technology is bridging the gap between the messy, unpredictable world of data and the elegant, rigid laws of nature, giving us tools that are both incredibly smart and scientifically sound. Thank you for your attention, and see you soon in the next video. Please let me know your opinion in the comment section.